From now on, let's double-click TechWiz LCD 2D. TechWiz LCD 2D window appears. The materials saved in TechWiz DB are displayed in DB Explorer in list form. If you double-click the particular material, you can check the DB information. The material can be easily inserted into the stack list by drag and drop method. The praise structure boundary is written on it. Please pay attention about this. Optical devices such as a polarizer and a retarder should be defined outside the structure boundary, like this. Since it is only involved in optical calculations and does not need the mesh generation for layers outside the structure boundary, they do not appear in the structure viewer. And you can utilize the icons such as add, delete, and up and down. And please look at the structure viewer. You can check the 2D structure directly defined in the stack list. And there is a properties window. You can define the properties of each layer. In the output, the status of the simulation can be checked. And on the top, there is a main menu and a toolbar, which can set the options for the project file or simulation. You can create a new project, load the previous project file, or save the current project file. Also, you can select a solver to analyze the LC distribution or choose an optical analysis method. I will talk about it later on in detail. If you click this Run button, the simulation starts, and there is an option. I will only describe a few of them. The first is about the General tab. If you check this option, you can enter the refractive index and calculation conditions for wavelength ranges other than visible light. Also, in maximum CPU core number used for calculation, you can set the number of CPU cores to use for parallel calculation. If you use about 4, you can check the calculation results quickly. And let's move on to the next tab, LC Server. The AC voltage is used when analyzing layers with high resistivity. If you check this button and then click OK. As an example, I will drag and drop this PI insulator layer. You can see that there is a conductivity and also there is a frequency. Therefore, you can define the conductivity and frequency values. And the next one is apply flexoelectric effect. You can set whether the flexoelectric effect is applied or not. If you check this option and click OK button, and then select the LC layer, you can enter Flexo ES and Flexo EV values. Lastly, let's click this Display tab. If you uncheck this Hide Adaptivity Properties, the adaptivity window will be activated on the LC layer. Adaptivity can set how the initial LC is oriented. You can enter a value between 0 and 1. And if you enter 0, the LC will be oriented according to the entered loading condition, regardless of the interface on the surface. For example, if I enter a pre-tilt angle as 90 degrees and adaptivity is 0, LC will be oriented like this. On the other hand, if you enter 1, the LC is aligned in accordance with the shape of the conformer surface and rubbing condition. For example, if I enter a pre-tilt degrees as 90 and adaptivity is 1, LC will be oriented like this. And for other options, please refer to the manual. Additionally, you can set the graphics output option called OpenGL. If the structure viewer does not work properly on the screen, please change the buffer status and check the structure viewer screen. Default is front and back. For the options, I will change as default except for the number of CPU cores. So far, we have looked at the big items of the 2D program. And let's design the simple example. When you design the cell structure, the first thing to do is creating a new project. Click this New button or click File and select New. Enter the name of a project and set the saved path. When checking Create Project Folder, the same folder as the project name is created and the project file is saved in that folder. I will check it and enter the name as EX, and then I will save it to the desktop. Please click OK button. So, I will generate this IPS example and explain some specific functions. In this example, there is no color filter. So if you want to check the results, including the color filter, please watch the video 7. And let's go back to the program. From now on, I will insert the layers from the bottom step by step. Except for the top and bottom polarizers, the first one is the bottom glass. Drag and drop the glass insulator in the material DB. On the right, property windows appear. You can check the name, color, thickness, electrical and optical properties, and other functions. As you can see, the thickness of glass layer is 20 micrometers. About 20 micrometers is recommended to reduce the calculation error for insulator layers. However, for the TN simulation, where the electrode does not have any pattern, it may be set to 1 micrometer. In this case, it is an IPS example, so I will enter the thickness as 20 micrometers. And substrate type should be set. If the layer is stacked, select stack. If the layer is a substrate, select substrate. If the material is being filled like LC, select fill. In other words, you can select the top and bottom substrates as substrate, LC as fill, and other layers as stack. Please note that property items are quite different depending on the substrate type. So defining the exact substrate type is very important. In this case, it is a glass substrate, so please select substrate. And there is a planarize option. Planarize is mainly used in dielectrics, and you can set the degree of planarization. Choose between no and yes. If you select no, the planarization option is not applied, and a conformer structure is generated like this. If you select yes, planarization option is applied. Also, you can set the DOP value from 0 to 1. When the value is close to 1, the structure will be perfectly planarized. On the other hand, when the value is 0, it is the same as selecting no, which has the conformer surface. However, in this example, we don't utilize the planarize option. The next one is a mesh condition. To generate a structure, mesh generation is very essential. TechWiz LCD uses a tetrahedral mesh where the length of one side is a unit length. Therefore, the smaller the unit length, the tighter the mesh is generated. So an accurate solution can be obtained. However, it has disadvantage of taking a long time to calculate. On the other hand, the unit length is large. The calculation time is very fast, but the accuracy is lowered. Therefore, proper unit length setting is required. Actually, if you click this button, you can set the mesh condition for all layers. However, in the properties, you can additionally set mesh conditions for each layer. Therefore, if you click no, it follows the simulation condition setting. And if you click yes, the layer follows the user-defined mesh condition. In this example, we will set a unified mesh condition in the Simulation Condition tab. So, for the glass layer, all of the information setting is done. The next ones are electrodes. To define the electrodes, I will zoom in this part. As you can see, the electrodes are arranged in the order of common, pixel, and common. So, common and pixel electrodes should be defined. Please drag and drop the two ITO materials. In this time, I will modify the layer name. You can change it in the properties or just double-click it. For the first one, I will change the name as COM, which means a common electrode. And as the same way, I will change it as pixel. So, comparing the two structures, they are totally different. This one is arranged in the form of common, pixel, and common. However, in this case, the electrodes are stacked. It means that we have to create mask. When you click the right mouse button, there are a lot of options. Most of all, to create a mask, select Add Mask or click this icon in the stack list. In this example, you can see that the common electrode requires 2 masks and pixel uses 1 mask. So I will add the mask. For the common, I will add 2 masks, and for the pixel, I will add 1 mask. And from now on, I will tell you the properties of a metal layer and how to set the mask information. I will check the layer properties first, and after that I will explain about mask properties. So let's click the metal layer. As you can see, the thickness of a common and pixel electrodes is 0.05 micrometers. So I will modify it. And the substrate type should be defined as stack. Most of the functions are the same as an insulator properties. Additionally, there is a resistivity and voltage condition. Since a voltage condition is quite important, I will explain it in detail after setting the mask. So let's move on to the mask properties. Please click the mask. So, in the taper model, you can choose the sidewall model among 7 taper models. When a specific taper model is selected, the taper type and taper value are activated. So there are 2 types. If you select the taper angle, you can input the angle. And if you select taper width, you can enter the width. I will use the default for the taper model information. The next one is mask properties. Reference and position consist of a pair. Reference is a reference point for entering the coordinates in creating a mask. If you click a reference, there are 2 types, left and center. And in the position, enter the exact position relative to the point selected in reference. Width is the width of the mask. So, I have 2 examples. I set width to 4 micrometers, reference to left, and position is 0 micrometer. In this case, the leftmost coordinate value of the mask will be 0 micrometer and the width will be 4 micrometer. How about setting width to 4 micrometers? Reference is center and position is 0. The center coordinate value of the mask will be 0 micrometer and the width is 4 micrometers. So if you look at this example, there is coordinate information for each electrode mask. I will define all mask references as left. Let's define the left common electrode first. Let's click the first common electrode mask. Reference is left, and position is 0 because the leftmost coordinate value is 0 micrometer. It ranges from 0 to 2 micrometers, so let's enter 2 micrometers for width. And in the same way, let's define the pixel electrode mask. Reference is left, and position is 11 because leftmost coordinate value is 11 micrometers. So I will enter 11. And since it is from 11 to 15 micrometers, so please enter 4 micrometers for width. And let's define the third common electrode mask. Reference is left, and position is 24. It is from 24 to 26 micrometers, so I will enter 2 micrometers for width. So far, I have defined all of the electrode masks. Let's check the generated mask structure in the structure viewer. The thickness of common and pixel electrodes is 0.05 micrometers, so it is too small. To check the mask structure properly, we have to control the viewer option. Please click this zoom window, and then I will zoom in, especially the mask structure part. So you can see that there are 3 types of masks. So in this way, the advantage of TechWiz LCD 2D is that you can input the structure information and check the generated structure directly through Structure Viewer. As I mentioned before, let's take a look at the voltage condition. Please click on the layer to check the layer properties. For the metal layer, you can set the voltage condition. You can see that there are 4 types: no bias, DC, sweep, and pulse signal. I will talk about them more detail. No bias means that it is a floating type, no voltage condition. DC is selected when a constant voltage is applied continuously from the start of the simulation until the end. And there is a sweep. By using comma or semicolon, multiple voltages can be applied. Also, when you want to define the voltage condition as a range, please enter in the form of like this. Lastly, if you select a pulse signal, you can use the signal dB predefined in TechWiz dB, or use the signal as a voltage condition by setting values. If DC or pulse signal is selected, additionally set time condition in simulation condition tab. For example, this is DC, so if you click this simulation condition tab, there is a time condition. Final time is the last time the simulation ends. Time step means the time interval for the simulation. It is recommended to use the default value of 0.1 millisecond. Output time is the output unit for the result. In this example, the common electrode is defined as DC 0 volts, and the pixel electrode should be applied with the voltage from 0 to 10 volts at 0.5 intervals. So, for the common electrode, I will use it as default because it is the same. And for the pixel electrode, I will change it as sweep and then set the range like this. The next one is the bottom PI. Please drag and drop the PI. The thickness of the PI is 0.08 micrometers, so I will change it. Also, you can check the electrical and optical properties. Let's talk about the LC. Please drag and drop the LC IPS. You can check the properties of LC. In this case, the thickness means the cell gap. Please enter 3.5 micrometers. It is a LC layer, so the substrate type should be set as fill. And the next one is the gap position. By using this function, you can set the coordinates of the point that is the basis for LC thickness. To specify a x coordinate, the gap position is set to yes and enter the position. For example, let's assume that I enter 1.5 micrometers. So at this point, a cell gap is formed. On the other hand, when the gap position is set to no, a cell gap is formed based on the mean point in the LC layer. Therefore, the cell gap can be different due to the gap position setting. In this example, please set the gap position as no. When the hardened option is set to yes, the lobbing condition is fixed regardless of the electric field, and the LC layer becomes a hardened LC layer. It acts like a compensation film. But we just use the default as no. And the next one is a mesh condition. If you click this mesh button, you can check the mesh being created. Especially, please note that at least 10 mesh lines within the LC layer should be created. Let's set the surface orientation. It is a TechWiz LCD 2D which can generate a 2D structure. For cross-sectional 2D simulation, the electrodes are always perpendicular to the screen. Accordingly, the lobbing angle of the LC should be set. In IPS, the electrode itself is tilted. Even though the initial orientation angle of the LC is 90 degrees, because of the tilted angle of the electrode, the lobbing angle of LC should be set as 80 degrees, not 90 degrees. Pre-tilt and azimuthal mean theta and phi angles respectively. So let's define the loving condition. I will enter a pre-tilt angle as 3 degrees. And for the azimuthal angle, I will enter 80 degrees. The next one is an anchoring condition. The motions of LC molecules can be calculated based on the anchoring strength. If the fixed is yes, the surface liquid crystals are fixed regardless of the electric field. If you click though, you can input the anchoring coefficient for each item and check the movement of LC molecules on the surface. However, in this case, I will use it as yes. Additionally, you can check the mechanical, electrical, and optical properties as well. You can modify its values as needed. And if you want to check the blue phase LC simulation, please click yes and then input the curl constant terms. However, also in this example, I will not consider the blue phase LC, so I will click no. So all of the conditions for LC layer are done. The next one is the top PI. Actually, it is the same as the bottom PI, so I will copy and paste it. To copy and paste the layer, use these two icons or press Ctrl C and Ctrl V. And the next one is the top glass. As the same way, this one is the same as the bottom glass, so I will copy and paste it too. And then let's take a look at the two polarizers. I already mentioned that optical devices such as polarizers should be defined out of the structure boundary. Please keep in mind this concept. At first, please drag and drop the polarizer out of the structure boundary. Let's check the bottom polarizer first. For polarizers, please pay attention to setting the phi angle. I will set the phi angle of the polarizer based on the O mode. In the loving condition of liquid crystal, the azimuthal angle is 80 degrees. TechWiz program sets the absorption axis as the reference. Therefore, I will define the phi angle of the bottom polarizer as 80 degrees. When setting the angle on TechWiz LCD, is that it should always be defined in terms of extraordinary orientation. The larger of KE and KO is the reference for the absorption axis. Look at the K values for the polarizer. KE is larger than KO. You can also check 80 degrees is the absorption axis. Since the polarizers are crossed by 90 degrees with each other, please enter -10 or 170 degrees for the top polarizer. I will enter -10 degrees. And for the thickness, it is essential to set the thickness according to the measured data. But in the TechWiz DB, I already mentioned that when you use the default polarizer in the material dB, I recommend to use 230 micrometer. So let's enter the thickness. You can also insert the light source on the external top or external bottom. There is a backlight unit on the external bottom part. Please go to the light source DB and just drag and drop the CCFL. You can check the properties of the light source. And the following ones are the wavelength and viewing angle conditions. It is the same as the method set in the voltage condition. Multiple values can be applied using comma or semicolon. When you define it as a range, please enter in the form of like this, or just select a particular step. For the wavelength condition, I will select 10 nanometer step. And for the viewing angle condition, theta at 10 degrees intervals and phi at 15 degrees intervals. So far, I have defined the stack list and properties for all layers. Additionally, we have to define the simulation condition. At first, simulation area. When defining mask, we use the simulation area from 0 to 26 micrometers. So I will enter the simulation area from 0 to 26. Next is the boundary condition. Setting the boundary condition is quite important because the calculation result can be different depending on the boundary condition. There are two types, periodic and Newman. When calculation area is periodically repeated, periodic is used. Newman means that the slope at the boundary is 0. If you designate the simulation area from 0 to 26 and set the boundary condition to periodic, you can see that the common and pixel lectures with a width of 4 micrometers are repeated as follows. So let's click periodic. In the offset angle, define the tilt angle for the electrode. An example using offset option will be discussed later. If you want to check the result using it, please watch the video 8. Calculate cap. Calculate cap can select whether to perform capacitance calculation. In this case, the unit is farad per meter. Next is the mesh condition. As I mentioned before, you can define the unit length in the properties for each layer. And in the simulation condition, you can set the mesh condition that applies to the entire layers. The smaller the unit length, the tighter the mesh is generated, so an accurate solution can be obtained. However, it has this advantage of taking a long time to calculate. On the other hand, if the unit length is large, the calculation time is very fast, but the accuracy is lowered. Therefore, proper unit length setting is required. So in this example, I will enter the unit length as 0.5 micrometers. Also, you can check the mesh to be generated by clicking this mesh button in the structure viewer. And once again, please keep in mind that there must be at least 10 mesh lines in the LC layer to check the accurate calculation results. And here is the time condition. You can set the time to run the simulation and output time. Since we used sweep in the voltage condition, you can see that only the time step is activated. It is time interval applied when the simulation is performed. I will use the default value. From now on, let's set the calculation method. TechWiz LCD 2D only offers a vector method. It is widely used due to the fast calculation speed. And you can select the optical analysis method. There are 4 types: extended Jones, Bellman, Mueller, and extended Jones hybrid. Extended Jones method uses a 2x2 matrix method to perform optical calculations. Only the reflection loss at the layer interface is considered. It means that extended Jones matrix method does not consider multi-reflection. So, calculation results can be obtained very quickly. The Bellman method uses a 4x4 matrix method. Multiple reflections between layers are considered. Accurate calculation results are obtained, but the calculation time is increased compared to the extended Jones matrix method. Mueller method calculates the result using the Mueller matrix. The calculation method is the same as the extended Jones matrix method. Lastly, extended Jones hybrid. By using this method, 3D optical analysis can be checked by considering the path of the input light. But please note that only a single viewing angle condition can be set. In this example, choose the extended Jones method for obtaining the results quickly. So, all simulation conditions are set. Please save this file. And to start the simulation, please click this Run button. In the confirm variable list, you can see the all conditions that we define. If it is OK, click the Continue button.